Now it's time to have you try some examples yourself, and then I'll go over a way of solving it. So, example 7 here is the cumulative world production of solar cells for generating electricity is predicted to be 58 times e to the 0.43 t thousand megawatts, where t is the number of years since 2013. Find the rate of change of this in 2023 and interpret your answer, which basically means they want you to state what that rate of change is telling you at that moment. They give you the other fun fact, which isn't really necessary for this problem, that 3,000 megawatts is enough to power a million homes. So take a moment here, see what you would do to answer this question. They are asking for a rate of change, so that should kind of indicate that there are certain things you should do to answer this question, but we'll go over it momentarily. So for this question here, um, you're being told that you have the power being generated from solar cells. So I'm gonna let that function be p. I'm gonna call it p of t, and they're saying that's 58 times e to the 0.43 t power. Now, looking for a rate of change, I also want to keep in mind that the year 2023 indicates that t is going to equal 10 when we're getting ready to use it. Now, the thing is, um, we will eventually put 10 into, a function, but if I put it into this function, what I would be getting is how many megawatts are being generated by solar cells in 2023. That's not what we're asked to find. Okay. It could have asked us to find it, but that's not what it asked us to find. It wants us to find the rate of change in 2023. And one thing you have to keep in mind is that whenever you're given a situation where there's a function involved and you have to do a derivative, you have to substitute at some point. You need to do the derivative function first and then substitute. Because if I put 10 in right now, I'm just going to get a number, and a derivative of any number is just 0. So I'm going to find out what p prime of t is. Well, 58 is a constant multiple, so that's just going to stick around for the ride. I'm going to do the derivative of e to the 0.43t. Now, I do have a function of t here. So I'm just going to rewrite the exponential function, e to the 0.43t. And then I'm going to do the derivative of 0.43t, which means that p prime of t is going to be 58 e to the 0.43t times the derivative of that, which would be 0.43. So to simplify, I would just take the 58 times 0.43, and I get 24.94 e to the 0.43t. This will give me the rate of change, at as long as I know what t is. And since I know t is 10, I'm going to plug that in. I get 24.94 e to the 0.43 times 10. And that's about equal to 1838.07. So basically what this means is that in the year 2023, it's expected that electric production by solar cells is increasing a rate of 1838 megawatts per year. Now that's not how much that's not how much it's generating that year. That means that at that moment where it's increasing, the production is increasing at a rate of that. So that answers that question and gives us the interpretation as well. So let's go on to example 8. The following function is a company's price function, where P is the price in dollars at which the quantity X in thousands will be sold. So P equals 4 minus the natural log of X is that function. They want you to find the revenue function, and you're given the hint that revenue is price times quantity. And B, you want to find the quantity and price that will maximize the revenue. So let me give you a moment to answer these questions. Well, the first one, the revenue function, since they told us and they helped us to remember the fact that I'm going to have price times the quantity. That means I'm going to have 4 minus the natural log of X times X. So R of X is going to equal 4X minus X, natural log X. Now it wants us to maximize the revenue. So we have this revenue function, and I can figure out the quantity that I would need to sell, produce and sell, whatever the case may be, in order to maximize the revenue. And therefore I can also figure out the price from that. Now, so for me to do that, since it's not like a typical function that I'm going to be able to know where the maximums and minimums are, and even be able to know if it has either of them, is I'm going to need to use a derivative. So I want to find what r prime of x is. So I'm going to take the derivative of this. So the 4x, the derivative of that is just 4 minus. Now I'm going to have a product in here, so I'm going to have first times the derivative of the second plus the second times the derivative of the first, which is just the derivative of x is 1. And I eventually want to be able to set that equal to 0. So as I simplify, x times 1 over x is just 1. This minus sign does get distributed, so I have 4 minus 1 minus the natural log of x, which is the same thing as having 3 minus the natural log of x. And I'm setting that equal to 0. The natural log of x would then be 3, so x would be e to the 3 power. Now I could run a second derivative test, and I really should. There's lack of space keeps from doing that. If I did the second derivative, just to give you a really quick rendition, and you could verify this yourself, I would end up with a negative 1 over x, which is always less than 0. Which means that generally this function, this revenue function, is concave down no matter what x is. Provided that x is a number in the domain, and actually it also makes sense because I can't have negative x because I can't make negative things. So, and I should look at e. It's better looking e than that. So I know it's concave down. It's going to have a maximum. So e to the 3 is about 20,000. Well, it's about 20.086. And since x is in thousands, that means that I'm going to have 20,086 items sold. the price four minus the natural log of e to the 3 power. Well, natural log and e would cancel, so I'm left with 4 minus 3, which equals 1. So basically, the company would need to sell 20,086 items at $1 each to maximize revenue. So there's the answer to that. Now, and of course, I mean, the maximum revenue itself, if they didn't ask for it, but you could calculate that really easy because I'm selling 20,086 items and it's $1 a piece. It's $20,086 in profit. So they're not saying what this is over time or what period of time, but there is that. So, and the last question that you're given. The percentage of the U.S. population with diabetes is given by the following function. D of x equals 0.96 plus 0.05 e to the x plus the natural log x. X is the number of decades past 1950. So D is a percentage of the U.S. population. X is number of decades past 1950. Based on this model, how would you expect this percentage to be rising or falling in 2020? And how fast is it rising or falling? Now, for the tell you a little honesty on this one here, I know if I'm looking for a rate of change, because that's going to tell me if it's rising or falling. If I'm going to need to do a derivative, and I can see here if I take a derivative, nothing here is going to become negative through the process of doing a derivative. If I was doing a second derivative, it might be a different story. But here, no. I mean, if I take a derivative, everything's going to be positive. So I can tell you right now it's going to be rising. Now, other functions, it's not going to be as overt. So, ultimately you're going to need to take the derivative, and even here we need to because it is asking us how fast it is rising. So I need an actual quantity than just to say, hey, it's rising. So since we're talking about the year 2020, I'm going to need an x value eventually. Well, that's 70 years past 1950, or 7 decades. And since x is the number of decades, that means x is going to be 7. But I do need to calculate a rate of change, so I'm going to calculate d prime of x. So the derivative of 0.96 is nothing. The derivative of 0.05 e to the x, well, I have a constant multiple, which just goes along for the ride. The derivative of e to the x is just e to the x. Plus, the derivative of the natural log of x is going to just be 1 over x. So there's my derivative function. And now I'm going to evaluate that at 7. So I'm going to have 0.05 e to the 7 plus 1 over 7. And when I calculate that out, give me a second here, I get about 54.97. So maybe about 55. So based off of this, in 2020, it is expected that the percentage of U.S. population with diabetes will be rising by about 55% per decade at that point. Always make sure that you're aware of the units being used. Since we're talking about number of decades, that's going to be per decade. So, I wouldn't be able to break it down any further unless I had it per year. But I don't have a function for that. So, but there is your answer for this question. So, if you have any additional questions, please make sure you ask about them in class. But now it's time for you to give the example problems from 4.3 a try. So go ahead to it, and I will see you in lecture. Have a good day.